If you mean f differentiable convex, then you just do gradient descent. Okay, happy. If I mean f and suddenly you have a constraint set C, what you do? Assume these are true, you do the same thing, you do the projection afterward. Now you mean f and plus a g. G is convex but not D-able. Okay, what you do? You have the same thing, but you do the prox. Okay, now if you look at all this thing I can change it. So now if you look at all these three problems, they have one thing in common. There's no constraint. This one have a constraint, right? But I move it here, so therefore there's no constraint here. There's no constraint here. What's the next one? The next one will be, then you may say, okay, then why not I do this? This is a problem. Why? Because if I do this, I will do prox x minus gradient. Okay, right? Then what will be the non-differentiable part? The non-differentiable part will be this thing. So you need to prox on this thing. And now I tell you a sad news. This problem is open problem. How do you compute this thing effectively? This is an open problem. What is this? Let's write it down. Remember, what is this? This is arc mean half x minus variable is c, okay, c plus gc. Now, if I have phi, this is phi, right? What is my phi here? G plus indicator function of d. So now I have this. Here's the problem. If I take differential optimality here, 0 belong to this whole thing. This part easy, okay? This part is the problem. Now I have this thing. Oh my gosh, bad. This is actually called free operator. So we have free thing. Now I change the name. I can even say, by the same argument, I call it H. These two are not differentiable. How do I mean this? I'm sorry. Proximal operator in general doesn't work. It works for special case, but not in general. And this actually is an open problem. How do you make a thing that you can prox three things and two things at the same time, and make sure you don't mess up with this? Then good. This is in general not doable. So what are the approach? So let me go back to here. This one, now you should know how to do it. This one, know how to do it. This one, know how to do it. Okay, now let's say what happens if I suddenly ax smaller than b. This is bad. So what's the solution? We have no choice to talk about this. So now let's talk about this. That's why we now go to do. So this is the first example. We have this. Okay, you may wonder, what the heck is this? This can be written in this form. Min f x plus g. Okay, now I said g something, not ax. But then I also add a thing, right? I call it gy, and then y is ax. Then now I have what? I have something exactly in this form. As I said, when you have three things, this is now problem, because this is very difficult. I'm not saying this is difficult mathematically. I'm saying computationally, because if you really want to solve this, you have supercomputer. You compute all the Minkowski sum and then search the zero inside this Minkowski sum for 100 years. Yeah, you solve this, but not good, right? So this is what I mean. Then what we do? Okay, then forget about primal. Do. For do, we need conjugate. Okay, let's recap, and we will have funny expression look like this. Okay, so let's go to what the heck is conjugate. Remember what I said? Function have two ways to express it. The first way is you write the graph. The second way is you write the tangent, and then you have this, right? Remember what this one? So this thing is the same as I have a bunch of line, right? So the second way to describe a function is you exactly use that bunch of line. The AP of everything is this function. This is the do description. Because you don't use x and fx, you are using y value, the intersect of this. So that's why you are in y. Okay, this is wrong notation, but anyway. This means x, and this is the variable is y, but anyway. So, and they are linear, straight line, so that's why you have inner product. But anyway, so what is do? This is called French-Chow conjugate. In I think PDE or physics or what, there's a Legendre transform. Actually, it's the same thing. So what is that? You have f, you minus it, and you soup it with this. Okay. Loosely speaking, we don't care about soup in, just use max min. Okay. So we have this, and the variable is on this. Okay. What's next? Then now I want to deal with this thing. Now we have Lagrangian, and I said why I don't like Lagrangian for constraint optimization, because if you want to study Lagrangian, you need duality. Without knowing duality conjugate, studying Lagrangian is very naive. So now I have this problem. What I'm going to do, I say this is y, then this is a new thing. Y is something auxiliary in the middle. So it's like this. I want to minimize x. This thing somehow linked to ax. Okay. What I do instead is I have x, I make a y here, y and x linked to ax. Now I minimize this, and now I minimize this too. In the end, it reach here. So I sacrifice what? Memory, because I now have to store more things, but I can solve it. So this is a trick. So now I have y with this. So now what's the problem? This is a problem. It's an optimization problem in equality constraint. So it's about mean f subject to g equals 0. The g here is ax minus y equals 0. Lagrangian multiply, I put it here, put a lambda here, right? Then now I do the same thing, exactly the same thing. So I put it inside. So now I have this. Okay? It doesn't matter if it's a plus or minus. So this is Lagrangian multiplier. And then what? Lagrangian multiplier is a what? Is a min-max problem. You min this and max on this. That's the penalty formulation I talked about last week, right? So now I want to do this. And what's the min? We have x, y. So we min x and min y. So I have to min x and min y here. Okay, now this term, I distribute it. I have two brackets. And now I even split them into each of on. This only on x, this only on y, nothing else. Now I have this part and this part. So this is a good thing. What does it mean? This is why duality is useful. Originally, think about it. I have min f plus g, and this g is a composition of ax. So actually I have min f plus g on x. So x touch f, touch g, and touch a. After I do this, min f only touch f and only touch a. The g is gone. This is convex. This is linear. Linear is convex. This thing is convex. Good. This is convex. This is linear. Linear is convex. Convex plus convex, convex. Good. And also this one now x only touch two things, not three things. Easier to do. This one only touch two things. Easier to do. So this thing supposedly should be easier to do. So I have this. Then what? Now I want to do conjugate. Let's go to conjugate. So this thing is this expression. Okay. Now I move a to the other side. Okay. And now this part I have a minus minus. I have this. Now I move this minus minus. This is a minus, right? I whole thing take a minus and take the minus out. So I have this thing and I make it max. I have this thing. This thing I move it to the other side and I multiply the whole thing by a minus sign and flip the sign. I have max. Why I do this? Well, because what is the soup of this? You max a linear term, subtract a function. This is called conjugate. So now I have this whole thing. This whole thing, something minus my function is conjugate. So now conjugate of this thing minus conjugate on negative nu on g. So this is a conjugate. So therefore, we now derive at this. And this exactly is the do problem in Lagrangian multiplier. Now you understand why when you do Lagrangian multiplier, when you do the nu variable, you always have something like something add something. It's gradient ascend, not descend, because you are max something going up. So now I have this. Then I just do the do update. What is this? This is gradient ascend on this funny function. So now I have the d problem. I call it d. Okay, and then min was min. Min is just negative of negative max. Then I can somehow change it back to familiar form. I don't want to deal with this crazy max of negative and negative, right? So now I change to this form, and I want argmin. Argmin means I don't care about this sign, because argmin, what is argmin? If this is my minimum, I multiply f by 9,000, it is still a minimum. So I don't care about a number. So I have this. So now it's good. What is good? This is the original problem. Now I have a do problem on the do variable, the min. So what is this? Gradient descent. So what does it mean? Now I have the following. I need to solve this. I will do gradient descent on x and y. What's the good thing about x and y? The good thing about x and y is convex. Convex, gradient descent. If this part is not differentiable, prox this on x. If this part is not differentiable on y, I prox this on y. So gradient descent on x, gradient descent on y. What about the dual? Gradient descent on the dual. And this becomes something called ADMM. So a simple form is something like this. Min f subject to ax equal b. Okay. What makes this funny? F can be non-differentiable. So we have to do proximal operator. Here's the standard trick. I have this, right? I add it in. And this is Lagrangian multiplier. So now I have min x max lambda. Okay? This is called saddle point problem. And when I do this, here's a tricky thing. These are details. I don't have time. We need to prove something called constraint quantification condition, saying solving S, solve P. So there's a relationship between S and P. The idea is this AX equal B need to be what? Linearly full rank, and therefore strong duality holds. These are detailed, no time to talk about. Let's assume this is true, okay? That means we can solve S and then solve P. Then this is the problem, okay? P is what? Constrained. That means actually you need to project onto AX equal B, or you do the prox on F, which can be difficult. But if you look at S, on X, nothing. No constraint here. On lambda, nothing. No constraint here. No need to worry about being invisible. Good. The only thing you need to be worried is just X and lambda are not good enough. So just run more gradient descent, gradient ascent. Okay. Now I have this. I want to solve X and then solve lambda. So basically what? I first mean this on X, fix lambda. And then I fix lambda. Fix X, mean lambda. Max lambda. Yes. If this is the first way. If I remove X into lambda or I remove lambda into X, this is called eliminating the variable. Then you give us something purely on dual variable. Okay. So this is the same thing. Okay, the same thing. Okay. So I have this. This is Lagrangian. This thing split with this. Come here. On X, rubbish. I don't care. But I put it here. Now I have this expression. A go to the other side. I have here. So now I have this thing. This everything is on X. I want to make the what? Conjugate. So I want to create a max. So I negative the whole thing, then I get a max. Okay? And conjugate is linear term minus function. Good. I have a minus. I have a linear term. I just change the position. I have this. So this back bracket is conjugate. Yeah. So this whole thing, you see, X is disappear. There's no X. So this is the dual problem. Max lambda on this. Then if I max lambda on this, there's a minus sign, right? Then it's the same as mean of this one with the minus sign and the linear term. Yeah. And then what is conjugate? Okay, this is talk about last time. Okay. Now, how do we solve the dual? We solve the dual by max the dual D, which looks like this form, which is just blah, 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 up to here. Okay. So now I have blah, 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 up to here. So I want to max this thing. Here's the thing. I didn't say F is differentiable. So F can be non-differentiable. I just said F is convex. So therefore, F can be looks like this, right? It can be lambda. It just happened here. That's why I have this. So lambda is the best value of max this thing. Okay, and suppose I find this lambda. Now what? I have the best lambda. Then what do? I have the best lambda. I absorb the best lambda in this expression. Then this is the best Lagrangian. I solve this, then I solve my X. That's like that. Okay, so this is like that. So then first we need to find the best lambda. What's the best lambda? You just solve this problem by what? Gradient descent, gradient ascent. Yeah, but this can be non-differentiable. Then proximal ascent. Yeah, something like that. So this is the idea. You have lambda. You just solve the thing on lambda only. And then you solve X using the best lambda. This is an abstract, useless algorithm. Why? This is an optimization problem. This is possible that this function is very difficult to maximize. So in principle, 3 can be very expensive. 4 can also be very expensive. So this actually is useless. This is why people start up with other methods. This is the starting point. Then what? How do we improve this useless algorithm? We do it like this. This is mean I solve this in one step. Then okay, then we don't solve it in one step, we make a for loop. So for each time, I get a better lambda, and then I get a better X, right? What is this? There's no for loop. Don't forget there's no for loop. This is just 4 steps. Find the L, find the D, solve 2 optimization problem, done, there's no for loop. Now I replace these 2 steps by 2 for loop, and if I can make sure my lambda and X getting closer to the solution, done. This is the idea. Then how do I do this gradient ascent? Suppose I can differentiate the on lambda. Okay. Then the question is this doable? Maybe it's not, because I said F is non-differentiable. Then maybe this is also non-differentiable. Who knows? And also, how do I get this? This is exactly the issue. We need to focus. So this is now differentiation of dual. So because F is convex, this is what? Have a negative of the conjugate. Conjugate is convex. Negative means it's concave. So, and we are doing max. So it's the same as what? Mean we like this because we want to go here. This is on max, so and it's negative, so it's like going up. So it's opposite. It's good. So therefore, we can go up unique if it is strongly concave. Okay, so actually we can do gradient ascent. So this is the opposite of going down, just going up. Okay, and if we can compute this is happy. So here's the thing: if this is unique, in other words, because we have Lagrangian, so that means we now have xy plane, x lambda plane. Then we have a surface, right? Not curve anymore. We have 2-dimensional thing. Okay, something like this. One is going up and one is going down. Here's a funny thing: it's possible you have a region that this part is going up, okay, but this part is going down, okay, it's a flat region. Then at this point, this is not differentiable, this point is not differentiable, this thing is not differentiable. Then you have problem on this. But let's assume this doesn't exist. That means we really have a surface. Then this one exists. Then I can just take derivative. What's derivative? Just d this thing and then put lambda is this. And actually, it just give you x minus b. Yeah. So therefore, gradient ascent is just 0 point gradient step size plus. Okay. These are detail. Okay. This detail is saying, basically the detail is that if this is not unique, for example, my surface looks like this, then this at this particular line, I have infinitely many x that are minimum at this point. Then at this point, this guy on lambda is not differentiable. Problem. Okay, but then we have to do subgradient. But let's make sure everything is differentiable. So now I have this thing. Well, let's go back to the big picture. This is the abstract algorithm. Useless. Hard to do. Now replace this by 2 for loop. This line means update x. Now I precisely make this clear. This line is just this. I swap their order, but doesn't matter. Now I have this. So now this looks like a little bit more ADMM. This is called dual extend LA, dual extend Lagrangian. So now I have to do this. How do I do this? Again, what is this thing? This is gradient descent on lambda. So I replace this by gradient descent on lambda, then I have what? Okay, so let me come to it. This is gradient descent on lambda. So I'm going to do minimize this on L, right? This thing, right? Then what? This L, we ignore this for a moment. Now I have this part. If I do gradient descent on this on L, I just take this. Because if this is differentiable, if this is not differentiable, I do this. Now, due to something, I add a quadratic term here. Adding a quadratic term here makes this whole thing strongly convex, and it makes it strictly convex. It is strictly convex, that means the solution at each step on x is unique because it's strictly convex. And this will be good for what? For the purpose of doing this part, because we want this to be unique. We don't want this to be in a set. So that's why people add a quadratic term. Then the here is the issue. This means what? This means I want x to be small, useless. What I want in the very beginning, I want ax equal b. Then why don't I put this as this thing? I put the ax equal b here. It's a penalty argument. I encourage this to be true. So I now have this. This is what? This is Lagrangian. This is something else. I add something here, then this augmentation, so this augmented Lagrangian with a parameter rho. And now this whole thing have a convexity. Yes. So now okay. Ignore detail, these are details, basically strong this corner. Now I have this thing. What's the big picture? Let me go back. Useless algorithm, replace it with a loop, make the step on lambda a little bit more precise, make the x problem strongly convex by introducing a new term. So now my x step have a rho here. Okay, good. This is called ALA, augmented Lagrangian. What happened to ADMM? Not yet ADMM. So this is the gradient of dual. Okay, these are details, no time. It's just convexity or blah blah blah. And then this again is the showing that the dual gradient is 1 over rho Lipschitz. Okay, so you can do step size. Then what? Now I have this thing. This is the expanded form. Okay, this is the expanded form. So this is the IO algorithm. For what? For min this substrate x b, this is the problem. I put this inside the problem. This is Lagrangian. This Lagrangian, I add the penalty of here to make the x part strongly convex. Then this is now augmented Lagrangian. Now I have this expression. What I do? Min this on x, mark this on lambda by what? Gradient descent on x, gradient except on lambda. Then this is called AMM. Okay? Up to here it's okay. Now suppose I have this. This is what we really want to talk about. I have min f, min g. G is now the setup usually is f differentiable, g not differentiable. And this is not gf, gy, it's gax. Now I do the splitting, I create a y so that I have this, so now I have free thing. Again, the Lagrangian. Okay, then what? You do the same thing. Min x, min y on this, on xy, and Lagrangian do parameter, do xn. Okay, now what? This problem is again have a problem. Why? Previously, I have this one. I just do gradient descent on x, no problem. But if I introduce a g here, this same step now is what? It's min xy coexist at the same time. This is not good. So what people do, these people many years ago say, we split it again by minimizing on x, fix y, and then minimizing y, fix x. And this is exactly ADMM. Okay, important, very important. I split them. Does not mean the algorithm split them is the approximate of this algorithm. I'm just splitting them. It's possible that if I really solve it like this, I join minimize x and y. The convergent solution may be different from I split them. Okay, this is by Jonathan. Basically, it's an early researcher on ADMM. Okay, so what is ADMM? This is the general form. I want to minimize a f plus g subject to, you can think of this as h. So there are three things. Min f g h. What's the big picture? Min f and g, we can do proximal gradient step. Now I'm doing min f g h. So prox will be more than 2 things, which is not doable. This is actually what the research, most new research still cannot do this problem. So we do dual problem. What's the dual problem? Put it inside, we have a Lagrangian, which looks like this thing. On xy is convex. I want strongly convex so that on lambda is unique the gradient. So I add a quadratic term. And now I have this thing. This is not easy to do in general. So I split them. So this is ADMM. So update x, update y, update lambda. What is update x? This, you just do what? Minimize this thing, fix all the other thing. This step is minimize this thing, fix all the other thing. This is what? Gradient extend. Yes. And then this is extra. What's the dual? You do the same thing. You make it max, then you have this expression. Okay. And then is the gradient gradient really this? Yes. Okay, no time to talk about it. And then this is the history. In the very early day, actually this thing come from Douglas Bradford splitting on solving heat equation, PDE again, many years ago. And then these two people say you should split. This is where ADMM is born, no theory. And then some researchers working make it better. And then these two basically provide the convergence analysis of the ADMM. And then this is a slide from the early contributor of ADMM. It's basically Douglas Bradford on what? On heat equation, I think. And then, yeah, 2D heat equation. And basically PDE. And later on, they make it to something called monotone operator. Okay, not detail. And then Gabe show that ADMM is just applied to this. Yeah, I just talk about it, right? And then later on, other people do other things. Okay, so this is the idea of ADMM. Then what's last? Why ADMM work? Okay, no time on this for detail. I just give you a very quick overview. So we want to min this, min FG subject to this thing. These are all the constraints. The Lagrangian, this part. The augmentation is this part. The algorithm is like this. The FG are convex. I didn't say they have to be differential. I just say convex. AB full rank. Okay. So this is nightmare. If you talk about gradient descent like this, proximal gradient descent, you have just a few bullet points. F converge, X converge, 0 belong to subdifferential at optimal point. That's it. We don't talk about second order optimality. We don't care. So we have just a free thing. Once we have this, oh my gosh, you have F converge. So this is the first thing. Point converge. So this is the second thing. This is what? This is new. Constraint converge. Do converge. Do value converge. Do variable converge. Optimality condition in subdifferential sense for the primal on X and for the primal on Y. Oh my gosh. So F converge, X converge, gradient converge. So you have F converge but primal and dual. X converge, but this is dual. Gradient converge. This also and then constraint converge. Yes. So the next 20 page is madness. No time. But if you want to do duality optimization, you can read and you see basically what's the argument. Again, it's just subdifferential convexity, and then bang. Okay, this takes you 1 week to read. Okay, and you see, I try to use so many colors so that even I can have a happier life. And basically, what it is to prove this kind of sentence. Okay, let me recap why we talk about subgradient. This is very much a lot of things, but actually in the end it's just subgradient. Yes. So therefore, subgradient optimality is so good. So let me recap. If you want to summarize everything in this 20 hours into one sentence, is this: X star belong to min F on X, of course, arcmin, if and only if 0 vector belong to subgradient of F at X star. That's it. This is the most important sentence. What does it mean? It means if my X star is a minimizer of F, of course this has to be convex, okay? Then I have this. What are the key points? Number one, I just said this is convex. I didn't say it's a differentiable. It can be not differentiable. And also, I didn't say what is F. It can be any F. It can be F plus G plus H. It can be indicator function. It can be constraint. Okay? It can be a deep neural net if it is convex. Okay? I also didn't say the solution is unique because you remember this is also convex, not differentiable. But everything here is a minimizer. Okay? So it just says X is a minimizer, convex. Of course, this hidden. What does it mean? Hidden. That means there exists X star. The solution says not empty. But anyway, this if and only if 0 is one of the subgradient at this point. This function not differentiable, but subgradient have 0. This line have no X component. The 0, -1 is the support of the AP graph exactly at this point. Okay, this is the most important. All the other things come from here, including this mess. Oh, no time, and that's the end. And if you want to read this, you can read it.